So I'm going to move along fairly quickly, but as usual, I encourage you to interrupt me and ask questions whenever, or if you happen to have anything that you'd like to know. So this is a tutorial on how to write a makefile and then how to use CMake to make makefiles for you. Okay, so essentially the first half, I will be just explaining, very slowly, step by step, what the makefile is and how it works. And then once I've explained everything about how you would make a makefile, I'm going to explain to you why you don't need to do it yourself and why you can use CMake to do it all for you. But at least then you'll understand what's going on, behind the scenes. And then when CMake is generating makefiles for you, you'll understand what they're doing. So I've aimed this at a level of somebody who's never, ever seen or written a makefile themselves. So if you have some experience with it, it might seem very easy. But if not, then you don't need to worry. We're going to really start from the beginning. Okay, so if you've got a repository ready, so I encourage you to have a look at the first README. So make file tutorial part 1, and you can go to the corresponding directory for part 1. Okay, so you should see the following files. Okay, so what do we have in this first directory? Okay, so we have some source code. So for these demonstrations, I have kept everything extremely simple, right? So the focus here is not on the code itself, but it's how we use Make and CMake to compile the project. So just to have something to look at, I've created a very small code that calculates the angular separation between two astrophysical objects, right? So you can imagine this being a very small part of a project that you're working on. But the steps you have to follow in order to compile it are exactly the same. So what do we have? So we have a file called main, which is essentially our executable script that we want to compile, and then a couple of dependencies for that. So one is a print statement that prints out the content, the distance that you measure, and another file called sphere_trig, which is short for spherical trigonometry, where we do the actual calculations for the distances. And then we have the corresponding header files for each of those. Okay, here I just show you some makefile syntax. You don't need to know all of this. I'll explain each symbol as it pops up in the examples. But here is just a kind of reference that you can come back to later if you forgot what one of the symbols means. And then there's also a link here for more details about makefile syntax. Okay, so let's start at the beginning. Okay, imagine I've given you this code and I say I want you to compile it. Now, on your first day programming in C++, you're probably going to see something like this with a hello world example or something like that, where they're going to say, okay, take your hello world source file and compile it using your C++ compiler, right? So we can essentially just copy and paste that line into terminal. And you see that we produce an executable that we can run, and you can see there it prints out our print statement and tells us the angular separation between Andromeda and the Horsehead Nebula. So our code is working. Fantastic. Okay, so that's all fine, and there's absolutely nothing wrong with doing it that way. But we could have done the exact same thing in a two-step process. So rather than just in a single line, we could have actually separately compiled. So let's remove this executable, and we could have run these 3 lines independently. And that would have produced these 3 object files. So we have print.o, sphere_trig.o, and main.o. Right. So for the moment, all you need to know is that the object file is kind of an intermediate step between the original source file and the final executable that you want to run. Now, the benefit of doing it this way, right? So essentially, in order to get our final product, we just need to take this final line and link those object files to the executable we want to build. And you can see now we get the same thing, which works in exactly the same way. So overall, the beginning to end, we end up with the exact same thing. Now, the benefit of doing it in this two-step process is that imagine I change something in spherical trigonometry. Now, in the first case, I would be rebuilding the entire code from scratch, having changed just one thing in one file. In this case, I say, well, I only changed spherical trigonometry. So all I need to do now is update the object file for spherical trigonometry and then relink it to the target executable, right? So now for a very small project like this, of course, it makes very little difference either way. But you can imagine if you had a huge project with 100 source files and 100 corresponding object files, and you only changed one of them, it would be a lot more convenient to only update what you've changed, right? So then you say, okay, well, of course, that makes my life a lot easier to have this two-step process. But of course, it's really painful to have to do all of this by hand, right? I don't want to have to build all of these object files and then link them and then keep track of all of them. So what's another thing we could do, right? So I'm just going to clean this. It's a little spoiler. We'll come back to that in a second. So another thing we could do is maybe we could just write a script that does all the steps for us. So if you want, you can scroll up and have a look at what's inside this script. Okay, you can see, in fact, it's exactly what I just had copied and pasted into the terminal before, but inside of a script. Okay, so nothing exciting going on there, but we can put that in a script that we can compile and run like that. And we've done exactly the same thing and it works. Fantastic. Now, the problem here is, of course, that we've actually now lost the benefit of having that two-step process because that script is doing the entire compilation. So even if we changed one file, when we rerun that script, we're still recompiling everything. So what we'd really like is something we can get the best of both worlds. We want something where we can have a two-step process where we can really only update the things we need, but we also want the automation of a script that we can just run and one step and it does everything for us. Well, that's exactly what the Makefile is designed for. Okay, so let's have a look at our first example. Okay, again, another little spoiler. So if you want, what you should do is have a look at the first Makefile, so the one that's just called Makefile. And I've added some comments into it there for you to show you, what each thing's doing, but we're just going to go through it piece by piece and look at what's going on. So Makefiles are composed of two things, essentially targets. So essentially a variable that you give followed by a colon, and dependencies, the things that follow your target. So essentially you have a target, it depends on something. And then on the second line, you're going to give the explicit build instructions for that target. So in order to build the executable main, I need all of these object files. And once I have these object files, the command for building it is the same line that we ran before, right? So this is exactly what we had copied and pasted into the terminal right at the beginning. Now, in order to, for this command to work, it has to say, okay, well, you depend on these object files, but what are these object files? Okay, so we need to explicitly define what the object file is. So we can say, okay, the object file spheretrig.o, it depends itself on the source file spheretrig.cpp, and the explicit command for doing that is the same command as before. So essentially what we end up with is the same 4 commands that we ran in the terminal, but now separated by this target dependency logic. Okay. At the end of the Makefile, we have an extra special command that we call clean, which simply removes object files and the executables that we build so that we can recompile the program. So there's this command on top called phony, and followed by the name of the target here. And what that's telling us is that this isn't a real target because clean doesn't have any dependencies. It's not something that we need to build. There's no actual build command. So essentially all we're doing is giving ourselves a special extra command that we can run from the Makefile. And this is just explicitly letting the Makefile know that this isn't a target. Okay, so how do we use this? Now, once we've put all of these pieces together, all we need to do is run the command make. And you can see what's actually running are those exact same 4 commands that we had before. And in the end, we end up with the executable that works exactly as before. So, okay, that's great, but in order to really demonstrate the benefit that we've got from this structure, we need to modify one of the source files so that we can see that we're only updating the object file that corresponds to that source file. So if I run the command touch, so touch isn't going to modify the contents of the file, but it will update the timestamp on the file, which basically will tell Makefile that, oh, this file has been edited. Okay, so we're going to trick Makefile into thinking that print.cpp has been edited. And now, if we simply rerun the command make, you can see that it's only regenerated the object file for print, and then done relinked all of the object files to the target binary executable. Okay, so now we really see that we've gotten the best of both worlds, right? We have the nice, easy, automated make compilation, and we also have the benefit of only really compiling what we need to compile. Okay, so hopefully now you understand what, like, the basic idea of what a makefile is and why it's useful. Okay, so now that you know that, let's think about some ways that we can improve our makefile just to make our lives easier. Okay, so for example 2, what we're going to do is we're going to make the makefile a bit more generic, right? So in the first case, we had written our target, its dependencies, and then we had the explicit build command for the exact, well, in this case, executable, and in this case, the object files. Well, what we can do is we can use these very ugly and very hard to understand make syntax to kind of just make it more generalized. So essentially what we have here is a reference to the target. So in the case our target is main, so this symbol will say, okay, I'm the target, so I'm main. And in this case, it's the dependencies. So in here, it will be all of these object files. So effectively, once you've defined this line is automatic from the previous line, right? So that's really useful, because essentially this is now something that we can generically reuse in almost any makefile, because it doesn't matter what the target is or what the dependencies are, it will give us the right build command, okay? And we can expand that logic to the object files as well, right? So here we have our spare trig object file, and we can replace the explicit call to the object with this make file syntax. Okay, so you can go back and look at the reference guide that I gave you to what these symbols exactly mean. But in this case, really the @ symbol means the target, the up symbol means all the dependencies, and the left kind of pointing arrow means the first dependency. Okay, so anyway, just as a proof of concept, we can show that this works. Since that we're using a different makefile, so by default, when you run the command make, it's looking for a file called makefile with either lowercase or a capital M. There are a few other things that it will potentially look for, but if we want to explicitly tell it to use a different makefile, all we need to do is pass the command -f and the name of the makefile we want to run. So in this case, let's just clean up what we had before. We're going to write make -f makefile 2. Right, and you see it works just as before, and our executable works. Okay, so all we did there was just made the makefile a little bit more generic. All right, so we can now push this a little bit further. Rather than explicitly defining the object files for our target executable, we could define a new variable just called obj. We could call this anything we like. And here we'll list out all of our objects that we're interested in. Now we can replace our target dependency call with this reference. And now you're starting to see that this part of our command is starting to look extremely generic. Okay, then rather than having a command for each one of the object files, right, it'd be nicer just to have a single command that does all of the object files. Well, in fact, we can do that. So what we can do is use this percentage symbol, which means do a lookup for things that match this pattern, which is .o. So basically all the .o files, all of my object files, all of the object files depend on the corresponding .cpp file. So essentially we can say, okay, all of my object files and all the corresponding .cpp files, and do this. So now we have an extremely generic command for building all of our objects. And again, we can prove that this works. Okay, so if we go up and look inside this makefile 3, just so I can show you, you can see it's a lot smaller than the original one, and we're getting the exact same performance and all the same benefits. Okay, so let's keep going on this logic. Let's make our life easier and easier, right? That's the whole point So what are some other things we could do? Okay, well, maybe we don't want to hard code the compiler that we're going to be using into our build command. So you see in the previous examples, we had G++, or what if I want to use a different compiler? Okay, so what we can do is we can define some variables in our make file. So we can define one called CXX, which will define our C++ compiler. So for the moment, we'll keep it as G++, but I could have put another one here. Maybe we want to add some compilation flags. Well, we can have a list of flags that we can add here. Then we can also start making things, again, a bit more abstract. We say, okay, let's define a variable that tells us where our source files are stored. And we'll store them in .src. Let's define a variable that will tell us what is the extension that I should be looking for in the source directory. So in this case, it's .cpp, but we could have had .c or .cc, or depending on what type of project you were building, you might have different type of source extensions. And then finally, rather than hard coding our final executable target into the build commands, let's just define a new variable called target where we specify what the target we want is. And then when we can update our build commands, they look like this, right? So essentially we have target dependency, right? So basically we have a reference to the target main and a reference to the object files for that. We have now reference to the compiler we want to use, the flags we want to use, and then we have references to the target and its dependency. So you can see now that this is starting to become less readable, but extremely generic, because I can essentially copy and paste this into a completely new project and get the exact same performance. All I need to do is explicitly tell the makefile what my target is. So in this case, it's called main. It could be called something else. And I have to tell it what my object files are. So now I have essentially a makefile I could really copy and paste between projects and do all the building very automatically. And I can even update my clean with this target reference. Again, let's have some evidence to prove. Running makefile 4, it still works. So now, we've got a much more generic and much more reusable makefile for different projects, but again, retaining all the same benefits of only having to recompile the object files for source files that I update. Okay, so let's take this one final step in this particular example. And let's add a build directory, because it's kind of ugly to have all of these object files and the executables mixed in with the root directory of the project. I'd rather have something a bit cleaner. So what I'll do is I'll define a new variable called buildir, and I'll specify a build directory. Great. Then the other thing that I had to do explicitly was tell the makefile what all of the object files were that were dependencies for my final target executable. Well, in fact, I can do this in an automated way. So now it starts to add a little bit more complexity to your makefile, but it still works, right? So what I can do is I can define a variable called src. It could be called anything. And what I'm going to do is tell it that I'm going to run a shell command. So basically, I'm going to tell bash to run the command find. Look in the source directory for any file which ends in the source extension, which is .cpp. So essentially look in the directory src for anything that ends in .cpp. Okay, that's fine. So once I've found those, I'm going to define the objects as the same root name, but instead of .cpp.o, and I'm going to store those .o files in my build directory. Okay, so essentially now, by having all of the source files that I need, knowing that all of those need a corresponding object file, I can automate the generation of the object files. And then I can have my final makefile version kind of look like this. So I'm going to define a new phony target called all. And the reason I'm going to do this is because imagine you had a project where you had more than one executable. I don't want to build just main. I want to build main, main 2, main 3, main 4, something like this. So I could have a target here called all, where I tell it to build this target and this target and this target, and then multiple commands for what it's supposed to do for each one of these targets. In this case, we still have just the one target, but it still fits into the same structure. Okay, so now we're saying, okay, I want you to build in the build directory a target called main with the object files that I've automatically found from the source files using the C compiler I've specified. And I want you to, in order to do so, you're going to have to build the object files also in the build directory using the source file in the source directory. Okay. So again, proof is in the pudding. We run it, and we can see in our build directory, we have produced all of the object files and our final executable, and we can do a final test to make sure our executable works, and it does, right? So now, if we go up and we go from the first make file that we started with, right, where you can see here, we really explicitly put everything almost exactly the same way we'd run it in the terminal manually, to example 5, where we have something that, you know, is, I would say, not easily readable, but very generic, right? Because now, if I wanted to reuse this make file for another project that was set up with the same structure, all I have to do is change this target to the name of the executable I need at the end, and I'm done, right? So that's pretty cool, in my opinion. Okay, any questions on this so far? No? Okay. Great. So let's move on to the next example. So you can click here at the bottom, continue, and that will take you to part 2. All right, and correspondingly, we should go to make part 2. Okay, so for this example, we're not adding a lot of complexity. It's just in the previous example, all we did was take the source files that we had and compile those. So in many cases, of course, you're going to be compiling a project with your own source files and some external library. Okay, so how do we add a library component into our makefile? Okay, so for the moment, you can look through this README if you want exact details on everything that's being done here. For the moment, all I want you to do is run this script, which is going to produce a static library using some of the components from the source files that we used in the previous example, okay? Once your static library is built, what we're doing to our makefile. So 1, we're adding a new variable called libdir, where we're going to specify where libraries are stored. So in this case, we've stored our libraries in lib, where you can see here, our libsphere.a library. Then we're going to specify what libraries we want to use from that lib directory. So just in case you're not familiar, if you have a library called libsphere.a, the corresponding command will be -l for lib, and the name of the library without the extension. So libsphere.a just becomes -l sphere. Okay. Then, also in this project, we've also been a little bit more meticulous about how we structured our project, and we moved the header files away from the source directory into an include directory. So now you can see in include, we have the header files separate from the source files. Okay? So now that we've added that complexity, how does that translate to our makefile? So we can take the same makefile that we just looked at, and what we're going to do is we're going to add onto the build commands for the target executable, the library. So we're going to pass in -l, capital L, the directory where our libraries are stored, and a list of the libraries we want, right? Where we can see exactly what those things are. And then for the object files, we're going to include a -i and the directory where the header files are stored, right? So basically these object files just depend on the sources and the corresponding headers. So we need to tell it where the headers are. And the final executable depends on these objects and the library that we're including, right? So basically that's all we've done to update this makefile. And if we run the command make, you can see the command actually gets run. We include, and here's our library. And then if we look in build, you can see it's there. And if we run it, it works. Okay, so now you can see, all right, now we've made it a little bit more like a realistic project by including both headers and libraries in separate directories. And imagine like almost all packages that you'll download that are written in C++ are going to include a bin, a lib, and an include directory, right? Where you've really structured things. And now you can start pointing your package, your project to these objects in order to use them in part of your code. Okay, is everybody happy with that? Wonderful. let's move on. Okay, so our last thing that we're going to look at for Makefiles by themselves is now building an external library that we haven't written ourselves, right? So an example of that would be something like cfits.io, right? So you've got a project, you've written a bunch of code for dealing with fits files, but you don't want to have to write all the fits handling yourself, right? That would be really painful. So would you say, okay, let's use a standard package, cfits.io, for example, where it can do all the IO for me, and all I have to do then is manipulate the objects, right? In order to do so, obviously I have to have cfits.io installed. So if you're on a Mac or using Conda, you can do that extremely easily. Otherwise, you can just run it, build it from source. Okay, so what are we doing to our Makefile now? So firstly, we have a slightly different project. So we have our new executable that we want to build is a file called list header, and it's going to depend on IO and IO, the IO header. Okay, so if we look at the Makefile, what are we doing? So we have more or less exactly the same structure we had before in the previous example, and we're adding on a few new variables here that we're going to go through step by step. Okay, so firstly, we're going to tell Makefile what is the library from cfits.io that we need for this project, all right? So the library we need is actually the lib cfits.io. We're going to tell the libs that they should include the cfits.io library. So the reason that this is separated is because imagine that you have a project that you have your own libraries and some external libraries where you can tell the libs here to include the cfits.io libraries plus your other libraries plus some other libraries, and then have a whole catalog of libraries that are required for this package. In this particular example, we're just using the cfits.io libraries. So next, we need to tell cfits.io where to look for the libraries, right? So we're going to define a variable called cfits.io root, which is not defined in the Makefile. So just keep this in mind. This is not defined in the Makefile. So this one is going to say, I'm going to look in this root directory for the lib directory. I'm going to look for headers in the include directory in this root directory. And then we can tell that the lib and includes to look in those cfits.io directories. So the reason that I haven't specified this is because imagine on one system that these libraries are going to be stored in one place, and another system they're going to be stored in a different place, right? So rather than hard coding a path into my Makefile, I'm going to basically have a variable that I can pass when running make in order to specify where this root directory is. So on my system, at least, when I install cfits.io with Homebrew, it's going to install cfits.io into this path. So now I can run the command rather than just make on its own. I can run this command, right? Where you can see now it's passed -i, and it's passed this include directory and the -l, and it's passed this directory with this library, which you can see has produced the following files, right, including the executable we want, and we can test that executable using an example its file, and you can see that we can read its header. So everything works. So that's pretty cool, right? So now we've added a bit of flexibility, because we could have a fairly generic Makefile that we could distribute with our project to other people, and they can specify the path to their cfits.io installation, right? So we don't have to hard code it into the Makefile and break it on every different computer that we try to build this code on. We can say, you've got everything set up. All you need to do is tell us where to find cfits.io, and it will work. Is that clear? Okay, and you can see that that's minimal addition of complexity to our Makefile. Okay, so that's all I wanted to say about Makefiles on themselves, right? So you see that it's not very complicated. The whole logic behind it is really just target dependencies, and the corresponding build instructions. And of course, in order to make that more generalizable, Make has its own very specific syntax for giving references to different types of objects. Like I said, this syntax is extremely ugly and very hard to read. For you and for people reading your Makefiles. So to that end, I would say don't write your own Makefile. we can go on to a service or a tool, let's say, that will make files for you, and it's a lot more user friendly. So this is a tool called CMake. It's become pretty much, I'd say, the standard in most of the C++ community for building projects nowadays. And basically, the reason for that is that not only does it, aid you in the process of producing a very generic makefile that can build very complex projects, but it also allows you to do a lot of other things on top of that. So we're going to talk about some of the basic things for now. But once you hopefully prove to you that it's worth your time to look into how to use CMake, you might invest in using this for your own projects in the future. Okay, so like Make in itself, CMake has its own syntax. Here I provide a link to the actual API for CMake on every command that I use in this tutorial. Of course, there are thousands more that I haven't included in this tutorial, simply wasn't time. But if you want to look up, you can just look up CMake syntax here and find a whole list of different things you can do. Okay, so to start things off, we're gonna go back to the simpler example of just building this spherical trigonometry project. Okay, so go to part one. Okay, so obviously, first thing you need to do is make sure you have CMake installed on your computer, right? So that can be done in one line on pretty much any Linux or Mac distribution. So that should be pretty trivial. So what do we have inside of our CMake? So instead of a file just called makefile, we have a file called CMake lists.txt, which looks something like this. So you can see, in order to build that first project, I have just 5 lines in this CMake list, right? So it's extremely simple, and let's have a look at what all of those things are. So first thing we're going to do is specify a minimum version of CMake that the user has to have installed. So this has already given us a huge jump in terms of what we can control with respect to just a standard makefile. So we can actually say that the user will not be able to build this project if they don't have the right version of CMake installed, because as CMake progresses, different features get added. If you include those features in your CMake and you don't specify a minimum version, then it will break, right? So now we can make the code less breakable by saying, okay, you have to have the right version of CMake before you even try to compile anything. And it will get a nice verbose message to the user if they don't. Second thing is we're just going to give a name for the project. It could be literally anything you want. That's pretty irrelevant. So then next, we're going to specify where the source files are located, right? So you remember in the CMake, we had our just source variable, and now we have a command that does it for us. We just specify the directory. So then we're going to specify what the source files are in this particular case. So we're going to define a variable called sources and list all the CPP files, right? So we're doing this in the kind of explicit way first, and then we'll go in the same way we did with the make, go to the more generic automated case. Okay, and then finally we have a command, which is very nice. So rather than have to write explicit build instructions, all we have to do is write the command add executable, name of the target executable we want, and the sources that it depends on. And basically from that, CMake will produce a makefile that will build the project. So the standard way to do this in CMake is to have a build directory, go to that build directory, and then run the command CMake and ... basically meaning look at the CMake lists file in the root directory. So running that, so you get a lot of nice information here. So one, it will tell you which C compiler it's using for the project. So the first thing you can notice is that if you're not using the compiler you expect to be using, that you've got right away that you know that you've made a mistake, and you can fix that before even trying to compile the project. And then, a few of the tests to check if your C compiler works, right? So this can also be useful because you could have multiple compilers and not all of them might be working properly. Okay, once that's run, you will see that it has produced a makefile, just as I explained. And if we look inside that makefile, you can see that there's a lot of stuff many of which you will be able to understand now, but probably way more information that's actually needed for this, but that's fine. We don't need to look at that anymore because CMake is taking care of it. So now all we need to do is run the command make. And then not only do we get this automated building, but we also get a nicer visualization of the building process with like a literal percentage of how much has been built. Okay, so you can see here we've built the same object files that we built in the previous example, and we built the same executable. Now we can test that, and it works. Fantastic, right? So you can see that that was way easier than the corresponding example, just writing the make file from scratch, right? All we need to do is learn the CMake syntax for each of those steps. Any questions so far? No? Okay, let's move on to part 2. Okay, so for part 2, now let's go again to a case where we've done a slightly better organization of our project. We've separated the source files from the header files and so on. So basically we want to make sure that we can find our header files. So we add the command include directories. So basically, which are the directories that have for include, and in this case it's just the directory include. And rather than specifying each individual .cpp file, we can tell it, look in the source directory for source files, all right? And essentially now it's going to look for all the CPP files for you automatically. So let's have a look at the whole CMake list. So in this case, again, minimum version, project name, all right? We don't really worry about those too much. Include directories are here, source directories are here, build the executable. Couldn't be easier. So let's have a look. Do the same process, go to our build directory, run CMake. Everything's fine, run make. Everything's fine. Does it run? It runs. Amazing. It's like magic. Any questions so far? No? Okay. Moving on to part 3. So in this case, okay, well, we need to be able to add libraries. So we had the example in the first case where we built a static library for libsphere. So let's see how we do the corresponding build with CMake. Okay. Okay, so what are we adding here? So firstly, we need to be able to find our libraries, all right? So we're going to literally write the command find library, tell it to find the library. So what do we want to find? We want to find sphere, and we want to look in the lib directory. And we're going to store those libraries into a variable called sphere lib. And then we're going to link those libraries to our target executable with the target linked library. So it's very explicit in CMake what the commands mean. So we're linking the libraries to our target with this command. So we're linking to main, and we're linking this library that we found. Okay, so again, if we look at the whole CMake list, we have almost exactly what we had before. We found our include directories, find our CPP files, we find our library, we build our executable, and then we link our libraries to our executable. Okay, so let's see if it works. It does. Right, so you can start to see how beneficial using CMake is and how easy it is to build these projects. Okay, so let's increase the complexity a teeny bit. Let's go to the case where we want to build a project with an external library. So let's do the fits.io example. Okay, so I think this is where we can start to see the real power of CMake compared to just doing something by hand in Make. So one of the things we can do is include a package that looks for packages for you, right? So basically, many packages will be distributed nowadays with a file that ends in .pc, which stands for package configuration. If the package has a .pc file, CMake can include this package automatically if it can find it in the paths. So basically there's this package config paths variable automatically set by CMake to look through default things like user and user local and so on. If you have it installed in a more local directory, then you need to add this to this path. But as long as CMake can find it, then it can find the package for you automatically. So you remember when we built this one with CMake, we made this variable called cfitsio root, where we had to give the explicit path to that package when we built the project, right? So in this case, what we're going to do is just going to say, this project depends on cfitsio, and this is a required dependency. So basically, if I can't find cfitsio, CMake is going to raise an error and tell you cfitsio is not installed on your system. I can't build the project. Right now, you start, again, exercise even more control on the building of your project. Okay, so then as before, we're going to specify where the include directories are. So now we can start using some CMake defined variables. So basically, if CMake finds this package, it's going to define for you certain variables, and you can look up what those variables are for certain packages online. And so it's going to tell us where the include directories for cfitsio are installed, where the libraries for cfitsio are, and then we can just, as before, build our executable and link the libraries to our executable, right? So again, the whole CMake project looks like this. So we have a new line here, which is including this package finder. So basically, it's just an extra dependency for CMake to look for packages. We're going to tell it to use this package to find cfitsio and make sure that it does find it. And then everything else is almost exactly the same as what we did before. Okay, so again, let's see if it works. Right, so right away you can see that there's some extra information in the verbose from CMake. And the most important thing it's telling you is that it found cfitsio, and it even tells you which version of cfitsio it found. So immediately, if you had multiple instances of cfitsio installed on your system, and you notice that it was the wrong version here, you could say, oops, it seems like CMake has found the wrong cfitsio. I better fix the path before building this project. Okay, and then finally, we can build it. Everything passed. We have our executable. And it works. Okay, so we've got one last example, and then we'll call it the day. So on part 5, so we're now going to take all of the complexity we've learned and put it together. So in many real C++ projects, you're not going to be building just a single executable. You're probably going to be building multiple executables from a huge library of sources, external libraries, internal libraries, and multiple header files, right? So, you know, it starts to become really complicated if you want to do this manually writing a make file. But again, CMake is very good at handling things like this. So what can we do? We can now, instead of explicitly putting our target executable in the add executable command, we can set a new environment variable, which we call target list, right? This could be called anything you want. And we're going to put all of the executable targets we want, right? So in this case, we're going to build both the spherical trigonometry example and the fits example simultaneously. So in this particular case, basically both main.cpp and listheader.cpp have a main method in the file, right? So if I left this alone, it would raise an error because it's like, oh, I'm trying to build, add these objects to something that has main, but this also has main, and I can't add main to main and so on. So basically what I'm going to do is, after I've automatically found all of my .cpp files, I'm just going to remove the target CPP files from that list so that they don't try to link to each other. Okay, so that's just a little cleanup step, right? You know, this would depend on the type of project you're doing. And then I can write a nice little loop here where I'm going to say for each target in the target list, I want you to build that target, and then I want you to link the libraries to that target, right? So now you could imagine all I have to do for building this project up and up is update this target list with all the executables I need. And it will find all of this .cpp files, it will find all of the headers, and it will find all of the libraries that you've specified automatically. Okay, So, and then finally, what I'm doing in this particular example is adding an extra step called install. Because imagine that you've built your project and you want a step where you can say, oh, okay, now that you've built all the executables, can you remove those to the bin directory on my system, please? Right? So you can add a step that does that for the user. So they do a make, and then they do a make install step, which will say, okay, I've built all the executables. Now they go to your bin, and now they're available on your whole system. Okay, so let's just have a look if this works. Well, first we can have a look at the full CMake list, right? So now it's a little bit more complicated than the very first example, but you can see same thing. We're looking for making sure cfits.io is installed. We're finding that spherical trigonometry library that we defined ourselves. We're making sure that we find the cfits.io headers and libraries. We're making sure we find all the CPP files. We're defining the targets we want to build. We're making sure those targets don't try to reference each other. And then we're building each of those targets, linking their libraries, and finally installing them to bin, right? So again, pretty straightforward. Okay, let's just see if everything works. Okay. And there you go. So it built list header and it built main. And just as a final proof of concept, that one works. And that one works. There you go. Any questions?
Yeah, one question. Could you go back to the CMake file?
Yeah.
This kind of processing for weight and so on.
Yeah.
Could you encapsulate it into kind of macro or something like this?
Yeah. So the thing is that, like, so what I've shown here is really kind of the simplest thing you can do with CMake. But if you look online, there's a huge amount of information about very complicated building things you can do with CMake, where you could say, I have a tricky project that's not going to compile in the easiest way. And then you can start putting lots of exceptions, and you can define, you know, an infinite number of variables and things. And so I have had projects where we've had Python call CMake, build a C++ files, build bindings from the C++ libraries to Python. And then at the end, you end up with everything that you can install with pip install. So, I mean, in fact, you can do a lot of really cool things. And I think that the main benefit is that if you imagine the amount of effort you put into just writing a make file from scratch, if you put that into CMake, you have, you know, infinitely more complexity with the same amount of effort put, right? And then what I would say is that definitely, if you learn nothing else at the end of the day, as at the bare minimum, you should have a make file for your project. And you should definitely not have like a hard-coded script or like expecting people to line by line compile your project. Okay, well, I will stop there, and thank you for your attention.
Thank you.